So today we are going to learn about the tangent theorem. That is the nothing but we have the one circle, that is the tangent. If we say the tangent is nothing but any line, any segment which touches the circle at a particular point, only the single point. That time we can say that it is a tangent. So as we can see that in the given tangent theorem, the segment OP in the to prove section, segment or radius OP perpendicular on the xy. So this thing we have to prove it. Okay, now we are going to come to the proof section. Okay, in the proof section, so you can see that we have the circle at a center, circle at center O, and tangent xy to the circle at a point P. You can see that here it's a this line segment touches the circle at a point P. So what we have to do, we have to prove that this segment OP, which is the perpendicular to the segment xy, then and only then we can say that this tangent is perpendicular to the radius OP. So what we have to do, we have to take point Q on xy other than P and join OQ like this. So we are taken here, it's a here this point should be the Q and join this segment this way. So you can say that this is segment OQ. Now the point Q must lie on the circle. Okay, so as we know that the point Q, this point must lie outside the circle. Why? Because you can see that if the, for example, must lie outside the circle, so if Q lie inside the circle, then xy will become a secant. As you know that secant is nothing but any segment which passes through the 2 point of the circle. Okay, so then we can say that the given segment is the secant. So that's why the Q point should not be lie inside the circle or on the circle. It should be the lie outside the circle. If the point Q lie inside the circle, then xy will become the secant and not a tangent. Not a tangent. So therefore we can say that OQ is longer than the radius, longer than the radius. So radius OQ, you can see here it's a OQ, which is the longer than the radius OP. Of the circle, that is OQ is greater than OP. Here it's a OP. You can see that the OQ is greater than the OP. Therefore, we can say that since this happen every point on the line except every point on the line xy other than P. Other than point P. So, OP is the shortest. OP is the shortest of all distances. Of point O to the point of xy. So, OP is the perpendicular to xy, as you can see in the given theorem. So, as we say that if the OQ, this OQ is the larger than the radius OP of the circle, that I write here OQ is greater than the OP. Since this happen on the every point on the segment xy other than the P, if there is any, we take the another point as well. So, that time you can see that every segment which is the greater than the radius OP, that means the OP is the shortest distance of the point O. You can see this the from the point O, OP is the shortest distance. Okay, shortest distance of the point O to the point of the xy. So, that's why the OP is the perpendicular. That's why we can say that this OP, which is the perpendicular to the segment xy. So, now what we have to do, we have to find out that, now you can see that what we have to do, we have to prove the tangent segment theorem. As we know that in the given circle, here are the two external tangents touches at a point P. Okay. So, what we have to do in the given theorem, this segment it's a P, you can see here it's a this point it's a D, and here it's a P and Q. So, what we have to do, we have to prove that this segment it's a PD and it's a QD, it should be the equal. Okay. So, before drawing or prove this theorem, what we have to do, we have to do one construction. Okay. This is nothing but, you can say that this should be the radius AP, the radius AP and AQ. So, what we have to do, we have to draw radius AP and AQ. Okay. Now, what we have to do in the proof section, you can see that in triangle PAD and triangle QAD. So, the segment AP which is the congruent to the segment AQ. Why? We can say that here it's a radii of the same circle. Same circle. Okay, you can everywhere the radius of the given circle should be same. So that's why we can say that the segment AB and segment AQ is the congruent, that is the radii of the same circles. Then the next one, it should be the segment AD. Okay, in the given this, it should be the 90 degree. So here it's a segment AD in triangle, as we say that it's a PAD, then QAD. Okay, this segment is equal because both are the radii of the same circle. Then the second one, it should be the segment AD, which is the congruent to the segment AD. Why? Because in this triangle and in this triangle, the segment AD is the common. So common, it's a common side or common segment. Then the next one, it should be the angle. Now you can see that angle APD, it's a angle APD, okay, which is the congruent, or you can say that it's equal. Then the angle AQD, which is equal to the 90 degree. Recently we see the tangent theorem. Okay, it's a tangent theorem. Therefore we can say that this triangle, that is a PAD, which is the congruent to the triangle, it should be the, we have the second triangle, that is the QA and D. Understand? By you can say that it's a hypotenuse side test, because these are the hypotenuse and this side is given. So we can say that this both triangles are congruent by hypotenuse side test. Okay, therefore we can say that segment DP is congruent, segment DP congruent to the segment QD, by we can say that it's a corresponding sides of congruent triangle. We can short in the short, that is a CS, corresponding sides of the congruent triangle. So in this way we have to understand that this is the tangent segment theorem. That means this segment should be congruent with each other. Okay, this theorem is proved by this way. Thank you for watching.